Good afternoon, everyone. Now we continue our meeting. Now we have this session, which the main topic will be gravitational lensing. And the first one is our co-organizer, Verónica Motta, which is going to talk about cosmological application of newly discovered gravitational lensed quasars. Thank you, Verónica.
Thank you, Edu. So I'm going to talk about some of the applications of cosmological applications of gravitational lensing. As you know, the standard model or the standard cosmological model has several cosmological parameters. Some of them describe the constitution of this universe, the dark matter, the dark energy, and others describe the dynamics of the universe, that is, for example, the Hubble constant. Once we have our cosmological model, we can describe the distance to an object using the redshift plus those cosmological parameters. But if we have any other means to estimate the distance, then we have an observation distance to the object. And combining both, we can constrain the cosmological parameters. So the quest has been to estimate some of those cosmological parameters through other means. More recently, we have seen a tension in the estimation of the Hubble constant that is related to the age of our universe, derived from different estimators. For example, the early universe, that is the CMB, for example, obtains an H0 value that is 5 sigma tension with those obtained from the local universe. For example, supernovae, gravitational lens, Cepheids, etc. So what is the problem with this tension? We don't know if the tension is due to, let's say, experimental errors when we're trying to measure this Hubble constant through this method, or is due to a new parameter or physical parameter that we need to add to this model, meaning, do we need to discard the lambda CDM and try another kind of universe? So I'm going to talk a little bit about gravitational lenses and how this can help understand what is the problem with this tension in the Hubble constant, and if we can solve it. So what is a gravitational lens? As you know, the light that comes from a background source could be deflected due to the presence of a gravitational potential, usually a lens, a galaxy, for example. So some of the properties of this gravitational lens or gravitational strong lensing system is that they see the whole gravitational potential, meaning we don't need to make assumptions about the light or the dark matter, and also provide a high magnification that helps you to see background sources, for example, acting as a lens, like an optical lens in the space. Some of the applications for these tools is, for example, we can understand or estimate the mass distribution inside the lens, giving estimations of the mass dark matter then inside the lens. We can also study the cosmological parameters. I think there is a talk after hours that has some of those applications, but we can also, for example, study the very faint and very far away sources. I invite you to see Carla's and Ramses' talk about some of these points. And tomorrow we have Alejandra's talk about supernovae with this strong lensing. So regarding the Hubble constant and how can we estimate it through strong lensing, first let me introduce you to the idea of time delay. In 1964, Refsdal proposed that using gravitational lens, we can estimate the Hubble constant. How? Because if you have the light coming from a background source, it's going to go through different paths. And the light is going to arrive then at different time to the observer. The time lag is what we call the time delay. And the time delay is related to this time lag through the equation that you see there. The equation has two components. One of them is related to the mass distribution or the gravitational potential, and the other one is related to the cosmology. So in that sense, the time delay is inversely proportional to the Hubble constant. So if we measure the time lag, we are able to get the Hubble constant. So this part is just associated to the mass model, meaning the gravitational potential. So the main point here is that if we measure the time delay, we have a single step in which we obtain the Hubble constant. The first time delay estimation with this method was made by another Uruguayan, Emilio Falco, in 1985. And since then, we have been able to measure it for other systems. Here, for example, I'm showing you 4 quadruple lens systems observed with the Hubble Space Telescope. So the images are in color, false color. And we need 2 ingredients to estimate the Hubble constant. First, we have to model the mass distribution in the lens, and then we have to follow up this, meaning we have to take images of these systems during a long time to get the light curves, and from there to obtain the time delay. What is a light curve? Here is an example. The problem is that we cannot get time in the huge telescope to follow up something, any object, during long periods of time that we need to obtain this time delay. So we usually get the, 1.2 meter telescope, for example, to do this follow-up. In this case, for example, image A1 and A2 are not able to be resolved by this small telescope. But if we get time in a little bit larger telescope, like a 2.2 meter, then we are able to resolve the 4 of them. And our task is to find a feature in those light curves that are able to give us an idea of the time lag. For example, here we can, by eye, just detect that there are some features there, and the difference in time of arrival with respect to one of the images is going to give us a time delay. So one of the advantages of having these quad systems is that we will get 3 time delays for the price of 1. Following one object, we get 3 time delays, 3 estimations of the Hubble constant. We have done this with 6 other systems that are shown there, and for each system we have 3 constraints, except in the one that we have 2 images. In that case, we only had 1. And because those systems are independent, then we can combine them and get a reduced error on the Hubble's constant estimation. Here is, in color, are the different estimations for each system, and in black you see the combined estimation of the Hubble constant with a narrower error. So our idea is to find or search for new quadruple lens systems. Why quads? Because for the price of 1, you get 3 H0 estimation. So the problem is that not all the quads are useful for this kind of measurement. So we need to find a lot to be able to discard or choose which one are the best. So we did that with a team of people, the community, the international community working in different things on gravitational lens, decided to combine our efforts in a project called time delay cosmography. So in this project, or in this collaboration, what we do is search for new quads and then try to follow them up and then try to find the Hubble constant. Here are 30 new quads that we have discovered in the past 4 years. And this is a major step for us because before we only had 15 quads. And now we are able to add 30 more. And from these 30, then we arrive to another problem, that we need to do a mass production of time delays calculation and mass models. So we need automatization of this process, that we are able to do it before one by one scientist. Now we need something to produce mass models and mass time delay. I invite you to see Felipe's talk about this. So this is one example of these new systems that we already have some like curves. And for the future, or our summary, is that we can use gravitational lens to estimate the Hubble constant. It will provide a high precision value comparable to the supernovae estimation. So far, we got from these 7 systems is a value that is in agreement with the supernovae measurements, but we are expecting the Rubin Observatory that is going to start next year, hopefully. And the Rubin Observatory is going to obtain thousands of quadruple lens systems. So we have to prepare for a flow of data. Thank you.
Questions, please.
Hi, thanks for the talk. So I have 2 questions. First, the first one is this of all the values for H0 that we have on the for all different, is on the higher end, is even higher than Cepheids and supernovae, right?
No, I think it's roughly in agreement with the supernovae data.
Yeah, but in the higher end, I think.
Yeah, but our error bar is larger,
Okay.
because we only have few systems.
Yeah.
We expect to reduce that to 1%. Now we have like 5% error. We expect to get down to 1% as soon as we get some of the other data.
And the other question was regarding the modeling. Do you, as you said, for different replications, are you assuming the same model for the gravitational potential, or you, for each of the images, let's say, you are assuming that maybe if they are not on the same line of sight, the lens and the background galaxy and the observer, maybe if they are not in the same line of sight, then it will be different for each of the images, right?
Yeah, well, we have to assume a gravitational potential for the lens. It's not obligatory because there are models that non-parametric model. But usually, for example, you can assume a Navarro-Franken-White, for example, or you can make a composite in which you describe the light of the galaxy, for example, using a Dvořákov profile, and then you add up the dark matter. But the model is more complicated than that, because the ones that I show use the arcs. I didn't mention that, but the arcs that connect all the images of the center of the quasar are is the image of the host galaxy. That give you more information, and you can do a better model. But we are also using, for example, the information about the external perturbation. For example, if the lens galaxy belongs to a group or a cluster, we can include that in the model.
Really great results, but also it's important in this way to be sure about that. So the errors you are mentioning are random uncertainties, I guess, 1.8. Are there systematics? Do you have systematics uncertainties?
Yes, we have, this is the errors. For each system, you have different errors because it provides for example, due to the model, and due to other uncertainties in the light curves, for example, there are other perturbations that we have. For the modelings, we have like 2 groups always. One that is working with the parametric model and blindly blinding, there is another group working with another model that is non-parametric. So I'm not personally working on the modeling, but those teams set a date in which they are going to disclose the final results and then check if they obtain the same Hubble constant with the models, right? So this is the blind analysis that we do to avoid that kind of systematic or bias in the choosing of the model.
Last question here. Sorry about other people that raised their hand.
It's a very quick question. What are the redshifts of the, not of the lenses, but of the object that is being lensed?
Usually I don't remember exactly for this system, but roughly the redshift of the lens is about 0.5 and the sources are around 2. But
So it's comparable with the redshift of the supernovae that are used also to measure that.
Yeah, but we have systems that are farther away, like 4, for example, but not necessarily one of these, right?
Thank you.
You're welcome.
So unfortunately, we don't have time for more questions. Let's thank Verónica again. And now, Carla. Can you use this one?
Hello, everyone. Thank you for giving me the opportunity of presenting my work. So my name is Carla Cornil-Baïotto. I come from France, and I'm a first-year PhD student at the Universidad de Valparaíso in Chile. And today, I'm going to introduce you to some of my research work related to strong lens modeling. So let me introduce you to the context of this research. As my supervisor said in her previous talk, gravitational lensing is the bending of the light emitted by a distant source as it passes through the gravitational potential of a foreground object called the lens. And throughout this presentation, we will focus on the lensing of distant galaxies by a massive foreground galaxy cluster, the strong lensing regime. And in the case of cluster lenses, lots of work have been done from lensing mass map and multi-wavelength analysis to constrain the physics of galaxy clusters and the properties of dark matter. Also, cluster lensing can give us hints on galaxy evolution and the study of the distant universe as these dense structures are acting as gravitational telescopes. And also, cluster lensing can be used to constrain cosmological parameters as it is sensitive to the geometry of the universe itself. You can see here on the right, the famous example of the supernova Restal. In addition to the Einstein Cross, so the supernova is seen 4 times, the host galaxy is also multiplying 3 times. And it really became famous recently for confirming time delay predictions. So the mapping from the unlensed to the lens coordinate, from the source to the image plane, can be described by the amplification matrix, where we introduce 2 terms. The convergence kappa, which describes the magnification of the images of the source, and the complex term shear, it's an external perturbation that corresponds to the stretching. And in this study, we aim to map the mass distribution, which is dominated by dark matter, of the core of this galaxy cluster. This cluster core hosts a notable strong lensing signature, a giant arc of about 14 arcseconds with 5 multiple images. And we identified 8 multiple images by their color and morphology. We did the lens modeling using a software called LensTool, which is a reference software for lens modeling, cluster lens modeling. And the first step is to identify what is the lens, what are the cluster lens, the cluster member galaxies. So for this purpose, a point source classification is done using the dual mode of the software source extractor on the 5 HSC filters of the cluster core. Then from the galaxies, we plot a galaxy color magnitude diagram and we identify the cluster member candidates on the red sequence, which has here a width of about between 0.1 and 0.2, sorry, on the color dimension. And after a visual selection is done, around 45 cluster members were included in the lensing potential. And in the central region of galaxy cluster, the geometry of the multiple image systems and the distribution of the cluster members provide information on the priors for the matter distribution. And it is therefore more appropriate to use so-called parametric lens modeling, parametric models. And here you can see we have news data on the core of this galaxy cluster. This data have been reduced by a collaborator from Durham University, and it allows us to have the spectroscopic redshift of the lens, and also to identify that we have here a galaxy in the background. We can see that it does not produce multiple images as does the bottom arc galaxies, and therefore we didn't include it in the lensing potential. And so in the case of parametric lens models, they are described by physical quantities, allows a direct interpretation of the results, and the lens tool software in practice takes 3 input files. So you have the list of the multiple images, here 8. We have the spectroscopic redshift from the muse data only for the giant arc. We have the list of all the cluster members, which are described by pseudo-isothermal ellipsoid mass distribution parameters. And in practice, we do not optimize all the 3 parameters or all the cluster members because they are too numerous. They are assumed to scale as follows, with the velocity dispersion, a core radius and a cut radius. And they are assumed to scale on the luminosity taken from a normal galaxy at the cluster redshift. And then the third input file is the one containing the model, where we can also say, okay, we would like to optimize a few major lenses. And each mass component, it is typical for galaxy cluster, is described by a dual pseudo-isothermal ellipsoid distribution. You have the formula, the general formula here. And throughout this study, we assume a flat lambda cold dark matter cosmology. And following the idea of Limousin et al. 2022, each dark matter halo component that we will introduce, each position of this dark matter halo will be constrained to the presence of at least one optical counterpart, so typically one bright elliptical or a group of galaxies. So here's the result of one of the lens models. The lines that you see here are the critical lines. In white, you have the critical line plot at the spectroscopic redshift of the giant arc. In red, it corresponds to the redshift, to the critical line plot at the redshift of the second system. It is the one predicted by the model. The signal to noise ratio of the muse data were not sufficient to have it, so this is also a free parameter. And in this model, so what we include in the total lensing potential, you can see here all the cluster member galaxies that I mentioned, a central dark matter halo that is typically the position is correspond to the position of the brightest cluster galaxy, the BCG. And here we decided to optimize the parameter of the BCG because we know this galaxy is a little bit special. It's not exactly like all the other galaxies of the cluster. And also we optimized the parameter of the bottom arc galaxy because it we can see produce additional multiple images. And so we can see that the model reproduces faithfully the observations because each lens image is separated by the associated critical lines. In this particular model, we can see that the second lens system has a predicted high redshift. The separation between the observed and predicted images is about 0.33 arc seconds, so this is a good model. But we can observe a high ellipticity for the central dark matter halo. I will talk about this later. And if you mentioned in the introduction, I also said that strong lensing has other very nice applications. So look at this very nice stretch large arc. Indeed, we can also use the lens model to reconstruct distant sources. And here, for this particular model, you can see the source reconstruction of the images. So the first step is to predict, to make image and source position prediction. For this, I use the same software lens tool. And then we process to the source reconstruction using a Python wrapper made by one of the collaborators. And each source is reconstructed from one lens image. In the case of a giant arc with different multiple images, all the images are merging along each critical line. So you won't have the total view of the galaxy, only a partial view of the source. In the case of, if I reconstruct the source from image 1.1, I almost see all the galaxy. And in the case of the image 1.3, I don't see all the galaxy, but what is nice, you can see it is more close to the critical line. So it is more magnified. And because it is more magnified, when we reconstruct the source, we have a much higher resolution. And we can see, we can distinguish like maybe 2 star-forming clubs in the image 1.3 when we reconstruct the source. And this is not the case on, when we reconstruct from another image, 1. So strong lensing is a powerful tool for studying highly magnified galaxies. And to have a realistic source reconstruction, it is important to have an accurate lens model. So the model you saw is one model among more than 20 we tried. And each model family is based on the number of optimized lenses in each given model. So you have here a summary of the different models. And in each of the models, we observed a high ellipticity for the central dark matter halo. Here I wrote the general expression of the lensing potential, including the cluster members that I mentioned, a few number of optimized lenses, so dark matter halos, specific galaxies, and in some of the model, we introduce also external shear. Okay. And as I mentioned, in all the model we obtain a very high ellipticity for the central dark matter halo. And so this motivated us to search for ancillary data on this galaxy cluster to understand what can be the cause of such unphysical ellipticity. And indeed, we are lucky because there is a very rich data set for this galaxy cluster. So you can see here the multi-wavelength analysis on very large scale. In green, you can see some HST philo view. So these are the images we used for the lens modeling. In red, there are the contours from the lensing mass map that we get from the lens model. And what is very interesting here, in the optical images, there are dark energy survey images on very large scale. We can distinguish a filamentary structure of galaxies. In addition to this, if you look at the blue contour, it corresponds to X-ray observation. There is a shift of 22 arcseconds between the BCV and the X-ray emission peak, which is quite big. And this is typically observed for extreme mergers. And in addition to this, in yellow, you can see Mercat-Elband observations. And we can observe we have radio diffuse emission and notably 2 radio relics. And these filamentary structures arise from synchro-2 emissions, and they are associated to cluster merger shocks. So this multi-wavelength analysis suggests that this cluster exists in a very extremely disturbed environment. And this could explain why we obtain such high ellipticity for the central dark matter halo, because in our case, we only consider one single lens. And in the case of the cluster merger scenario, it is highly likely that there are substructures at different redshift. So to conclude, we successfully mapped the mass distribution of this galaxy cluster, and his high disturbance observed from the multi-wavelength analysis could explain what the model predicts a high ellipticity for the central dark matter halo. And I hope I convinced you how powerful is strong lensing. It has a wide range of applications. In this talk, we saw that it could be used for mapping the mass distribution of dark matter in dense regions of galaxy cluster. We can use it to reconstruct distance lens sources and study highly magnified galaxies in great detail. In the next talk, Felipe Avila from the same research group is going to talk about the application of microlensing in the study of quasar. Thank you for your attention.
Questions?
Thank you. First of all, great talk. And you talked about the reconstruction of the source. I wonder what you can learn from there, because you didn't touch much on, like, I will guess morphology, or what else can you learn from the reconstructed source?
So we can learn two interesting things. When you perform source reconstruction, you will directly use the geometric transformation provided by the lens model. You can learn where is located the source in the sky plane, and you can learn how looks your source at the end, what is the morphology of your galaxy. Mm-hmm. And this is interesting, but it is true that if you are looking to resolve, for instance, star-forming clumps, it is more interesting to just study it from the image plane, because in the image plane, it will be very stretched and you will have access to a lot of detail and a great resolution.
Okay, thank you.
We have time for another question.
Did you compare your results with other lensing models that have been developed in the community?
For this galaxy cluster?
Yeah.
So there is a paper on this, but it was not really focused on the model of this galaxy cluster. It was from a study of 8 giant arcs, and a quick lens model have been done on it. And I also use it to start. But this model has some problems, and I remember it was just to have a quick estimation of the magnification rates for the specific study of giant arcs. And in my case, I really tried to explore why we had a very high ellipticity. And so I don't have the time to show everything in this talk because it's too short, but we really focus the study more on the galaxy cluster and all this high disturbance environment we saw. We also map the photometric distributions of the entire cluster to try to search for substructures. But there is not really a lot of model to compare.
And the magnification maps are going to be available in some moment?
It depends on the model, but I know there is all the area with the giant arc, the magnification rates are higher than 10. But after, it depends on the model. From some of the model, we obtain magnification rate up to 30 for some of the images on the bottom of the arc. So it depends, yeah.
Okay, so let's thank Carla again.
Thank you.
And we move to our next talk.
Hola, hola.
Yeah. It's fine. That's yours.
Great. Okay. Ahí se. Ya. Creo que estás en el Zoom. Ok. Hola, buenas tardes, muchas gracias por venir. Soy Felipe Avila, soy estudiante de doctorado de segundo año en la Universidad del Paraíso y voy a presentar un poco sobre mi trabajo. Voy a cambiar a inglés ahora. Okay, my work is Microlensing scale estimation for 190 lensing quasars. As my tutor says, the number of quasar lensing is going faster than ever in the last 10 years. As you can see for this histogram, the numbers is also almost duplicate in the last 10 years. That is great because, as my tutor say, the cosmology is passing through attention, they call it Hubble constant tension. That means depending of the sample you use to estimate the Hubble constant, you will obtain a different value. For this, the addition of a new method to try to estimate this constant will be great. In your case, we use gravitational lensing using the equation of Repthal, and we observe the object. We have to observe the object for a long time. We have to make photometric following of the objects for a long time to try to estimate the Hubble constant. But this following have problems because it can be affected for systematics as microlensing. And what is microlensing and how affect the light curves? Well, here we have a typical scheme of the quasar lens effect. Here you have your source. The source is lentified for your galaxy, and you obtain 4 images of your source. And also, this image can be affected again for lensed, but this time for the stars in the external part of the lensed galaxy. This is called microlensing. And this affect the light curves you obtain for the following. And finally, this add error to your estimation of the Hubble constant. But also, microlensing can be useful for obtaining parameters of the source, as Ramses will tell you in the next talk. So the objective of my work is try to estimate the time scales of this microlensing. Here you can observe a magnification map in where you see the different zones in the source plane, in where in the blue part are zones with less magnifications, and the clear part are zones with higher magnifications. So what we want to do? We want to estimate the 2 scales associated to the microlensing. One is associated to the source of the lens system, another associated to the size of the microlens. In this case, stars, and both are divided by the affected velocity of the source. So to perform this, we have to pass for 3 steps. The first step is try to make a census of the objects disponible in the literature. Why? Because your community is not too big, and we don't have a very big database of objects. So we have to go and try to obtain the data enough to try to make your modeling. And what is the data we need is the photometric of the systems and the astrometric of the systems. Then with that information, we will perform a modeling using lens model for Keaton that is a very well tested modeling program. And finally, we can estimate your time scales. So the first step to do this, we first start for the bigger database available is the Castle survey. We have a more or less 100 systems, and then we move to the dark energy survey that is still working in finding new systems. And with that, we hope to move to Gravitational quasar database. That is a source with is a database that only have the reference of the system. So we have to go one by one in the literature to try to obtain the photometry and astrometry of the system. In the end, we obtain 230 quasar laser system known. So then we have to move to the modeling system. Because we have a lot of system, it's not easy to model one by one. So we create a simple automatic pipeline to try to model the system. So in the first step, we will model your system using a singular isothermal isosphere for the doubles and singular isothermal ellipsoid for the quads. In the case the difference between the obtained image and the real image is less than 0.01 arcseconds, we will accept your system. This is a case in your modeling works. How you can observe the separation between the image and the obtained image is is too small, so it can be accepted as a good model. In the case your modeling doesn't work, we have to add some type of external perturbations to try to improve your modeling. In this case, we'll only use shear. That is the most typical type of external perturbation can be used. And then we apply again your filter in order to try to model, to try to accept or not your modeling. In the case your modeling works, it will pass to an uncertainty calculation that is a simple Markov chain Monte Carlo with using the parameters of the modeling as the priors. So here you can observe a system with modeling with a singular isothermal isosphere and a singular isothermal isosphere plus shear. But in this image, it's difficult to observe the real difference between the separation between the real and the obtained image. So what we do here is a simple zoom in that zone, and you can observe from I can observe it, but I expect you can observe from the TV. But here you can observe for the singular isothermal isosphere is very big comparison with the singular isothermal isosphere plus shear. But also exist cases in where your simple modeling doesn't work. So that is the case of this system. You can observe here that the separation between the obtained image and the real image is too big to be accepted for your modeling. This is the reason why this doesn't work is because the effect of the shear is not enough to model the external perturbation from this galaxy here. So yes, you can model this, but with your modeling, it can be done. So then we finally calculate your Microlensing time scales. Here you can observe your results. This is not the first time that this calculus is done. The first time was made for Mosquera and Kochanik in 2011. They obtained a median value of 21 years. We obtained a little less, but we are in agreement with the big difference between what they did and what we do is we model all the system and different become in the difference with them, because they doesn't model all the system. They only try to do it with models in the literature. Also your sample is double. Then for the time scale associated to the source time scale, we have a less time, but also in agreement with 8 months in median. But Microlensing this calculation is not only useful to know the time scales. Also, we can know how much affect the microlensing the light curves. This is done by the calculation of the microlens amplitude and amplitude. How you can observe, the most of the system are the normal part of the microlensing amplitude, and this amplitude goes bigger to the low part of the plot. With these objects are expected to be affected more for microlensing than the others. So in the beginning of the talk, I just speak about how you can calculate the Hubble constant using the quasar lensing. But the system that are used for this are only in this part of this plot. So the idea for my next step in this investigation is try to study the objects in the zone of microlensing, bigger microlensing amplitude and the low microlensing amplitude. So for this, we start observing these systems and try to prove. So these are my conclusions. Thanks.
Okay, we have time for questions. Questions, anyone?
Well, sorry if I didn't understand. I get lost. But what would be the physical cause of the variation of this microlensing?
You will have errors in the amplitude. That means when you try to estimate the Hubble constant, you need to have certainty of what you are observing. So if you are observing a system with microlensing, you are observing a fake amplitude, fake magnification of the original system. So you will have a magnification or the magnification. Yeah, that is.
So I have a question. So that's a question I want to ask to Verónica, but I had no time, and I can take the opportunity to have time here. So you just mentioned one factor that can complicate the estimation of H0 from lenses, which is microlensing, and as well you mentioned the external shear, which sometimes we don't have a lot of constraints for that. And the model of the lens as a whole is a source of systematic uncertainties. So how does the study you do contribute to shrink those uncertainties?
Well, if you are observing a system that is probably have the possibility of microlensing,
so because using the fluxes would make the model more consistent.
Yeah.
And then get to comment.
Yeah, because what Felipe does is the scale. So his result says every 8 months I should see a scale of microlensing. So the curve is going to change, for example, every 8 months, probably for these systems. It's not sure. But the light curves that are used to estimate the Hubble constant add a microlensing shape to the curve to account for that. But we are not sure that that is microlensing. It might be another error, for example. What Felipe is trying to do is he estimate the scale, and now it's going to the telescope to test if this assumption is correct. So when we detect the microlensing, we just say, okay, this is the microlensing for this system, and this is the amount of microlensing that we have. So then we can go to the curve and correct it, but with something that we know.
So we have time for one more question. So if not, let's think again. So João Pedro now. João Paulo, sorry.
Can you hear me? Is this working? Yeah. Okay, so good afternoon, everyone. I'm João. I am a graduate student at the Brazilian Center for Physics Research in Rio de Janeiro, Brazil. I'm currently supervised by Martin and James Nightingale. So today I'm going to talk a little bit about the constraints on modified gravity, especially on ground-based images and modeling and yeah. So these are a few contributors of this work, and one of the amazing systems which is currently in our sample. Okay, so I would like to begin by the big picture of the cosmology. So this is an illustration of our current understanding of the universe. So under what we call the lambda CDM model. So the way we understand is that the universe began with a Big Bang, and then with a slow pace phase for a while, and then the universe that we see today. But if you see carefully this image, there's something a bit weird happening here at the late stage of the universe, which is decelerate expansion rate. So there's basically two ways to solve this problem. One is to include another component in the theory, which we call dark energy. So if you ask how much dark energy we need to explain, it's actually a lot, almost 70%. And we also, we also have to have this dark matter to explain star formation and galaxy formation at this age. So another way to solve this problem is basically to modify the theory. So we can consider, for example, a more generic perturbation on the lambda CDM model metric. So if we do this, we will end up with these two potentials, phi and psi. And in the way that when these two potentials are the same, we can recover GR. But yeah, things start to be interesting when these two potentials are not the same, right? And we can define this ratio, which we call the gamma parameter, where we can, measure and infer this difference between these two potentials. So one way to solve this problem is to consider the movement of the mass and massless particles. So this is the equation for the mass particles, which is basically will give the Jeans equation or the kinematics for example, the stars in a galaxy. And this is the equation for the massless particles, which is basically one of the equations which is associated with the lens. So the idea here is to find an observable where we can test these two approaches and infer the potentials, right? And this observable is actually the lens. So Verónica already made an amazing introduction about the lensing. I just want to highlight that the lensing configuration that we are going to consider is the galaxy-galaxy lens, or the galaxy-galaxy scale, where the foreground object and the background object are galaxies. So this is basically the state of the art of the gamma inferences. We can basically have two approaches. One is to have a large sample of lenses. They can be basically an heterogenic sample. Then infer the gamma parameter and build any statistics over all of these estimations. Another way another approach is to have a highly precise modeling of one single system, measure for example the velocity dispersions have a spatially resolved use spatially resolved instruments to measure the velocity dispersions in the cutouts. But I think the key point is that all of these works are basically using space-based imaging data. So I'm showing a little about these lenses that is currently being used, and there is sort of a contrast with the next generation of data, which is will be given by the Rubin or the LSST. So just to give a scale of this survey, there will be a large amount of data, almost 15 terabytes per night along the 10 years of operation. It will cover almost 0.5% of the sky, and we'll observe many times each object. So as Verónica already showed, we can basically make a movie of the sky and detect anomalies, time transients as quasars, as Verónica already said. So if we this is the number of discovered lenses in past generation surveys. And if we could put in this bar plot the number of expected lenses from the Rubin, we will end up with something like this. So we can barely see the number of lenses in past generation surveys. So there's a need to have automated ways to analyze this data, to model, and so on. This is the collaboration map of the LSST. There will be a special collaboration for the strong lensing. So just to give an idea of the importance of the strong lensing for the next years in cosmology. Oh yeah, this is the log scale plot. So in order to prepare for the next generation survey, our group have collected a lot of candidates of lenses in ground-based surveys. There is thousands of candidates of lenses in ground-based imaging surveys. I'm showing a few of them. So we also have cross-match with spectroscopic and photometric data. So for a few lenses, we have redshift for the lens and the source. It's very useful, this sample. We have hundreds of single lens galaxies, so they are more probable to be galaxy-galaxy lenses. We also have aggregated data, which means that for a few systems, we have more surveys, which means that we can choose, for example, the higher resolution image to model, for example. So yeah, these are a few lenses of our sample and the sky coverage. This is part of the project of Renan Oliveira, which is a PhD student of our group. So yeah, we have a lot of lenses and we want to model these lenses. So this is the modeling workflow that we use to model. The first part is basically working with astronomical data. So I'm not going to talk much about this section. I'm going to dive more in the modeling pipeline itself. So yeah, these are the components of the model that we use. To model the lens mass, we use a power law, which is given by this equation. We also consider an external shear, which gives an information of the weak lensing along the line of sight. To model the lens light, we use a composition of Gaussian profiles, so a multi-Gaussian expansion, and you can see the contours in this image. So to model the source, we use something which is a bit more complex, which is the adaptive pixelization. So the basic idea of the adaptive pixelization is to map the image in plane pixels into a non-regular source plane. Here we use a Voronoi, a grid. So the idea is to construct the Bayesian objects. Here we show the chi-squared, which is the standard chi-square of when you compare the data in the model. And there's also a contribution of another terms, which is basically to avoid overfitting of your data. So here we can see a few examples of the source reconstructions. And there's also an amazing example on simulated data where the reconstruction can basically reconstruct the shape of the original of the galaxy. So this give an idea of how the high redshift sources can be studied. Okay, so the modeling pipeline. This is the modeling pipeline that we use, which is it's currently being built up on the Baïotto lens. It's a very intuitive open source code, so you can easily access. There are a lot of lectures in the repository, so it's very easy to try. So we begin with a source parametric fit just to infer the lens mass parameters. So we use this this more simple model. So we proceed to the next stage where we fit this non-regular source reconstruction. We then refit the lens mass from the previous phases. We then refit the lens light. So if you go back, we can see that the residuals are way better at this stage, and we end up our pipeline by fitting a power law component, which I showed earlier. Okay, so with this pipeline, we already modeled a large sample of lenses. I'm showing a few of them in this slide. Okay, so we have model information, and we also want information about the kinematics of these lenses. So here we prepared a small sample of 21 gravitational lenses. Here I'm showing a few of these amazing images. And these are the spectras that we obtained. This horizontal line is basically the spectra for the lens. And not sure if you'll be able to see, but there's a faint line, which is the spectra for the source. So there's a lot of analysis going on here, and to obtain these final reduced spectra. This was made by Ingrid Belotto and her supervisor, Eduardo Cipriano. By the way, there's someone which is very similar to him. I'm not sure if you already see, but yeah. So we as we model the power law components, we directly infer the slope of the mass distribution. There's a whole discussion about how dark matter and visible matter combine and follow this simple rule of 1 over r squared. And this is our constraints on the slope of the mass distribution. I think the key point of this graph is basically that all of these works were basically on analysis of space-based data, and these results is basically one of the first results on ground-based images. So it's a very interesting work. And finally, the constraints on the modified gravity. Okay. So these are the PDFs, especially the PDF on the gamma. We obtained 68% in agreement with GR, so no need to worry. You can still use general relativity. It's also a fully ground-based analysis, which is another special key point of this work. And we also use it priors on the modeling slope and the light, which is something a bit more technical, but yeah. So I think I'm running out of time, so I just display this, and thanks everyone.
Thank you. Questions?
Yes, nice workshop. I have a question. Usually the arcs are kind of hard to find the redshift for those. How hard is to, I don't know if you use, for the source, you use photometric redshift, or you just use the ones that had a confirmed spectroscopic redshift?
Yeah, so for the modeling, the redshift it's not much important, because all of the modeling parameters doesn't depend on the redshift. But yeah, for the constraints on the modified gravity, we need to have this redshift. So with this work, with the follow-up, we were able to measure, I think, 6 redshifts, spectroscopic redshifts, and we use the spectroscopic redshifts to make the modified gravity constraints. But yeah, for the other systems, we just used the photometrics, which were available. Yeah.
More questions?
Nice talk, thanks. It's just a nice question. Your parameter gamma, which is tells you how much apart is from GR, right?
Yeah.
What is interpretation? What is the difference that you have gamma bigger than 1 than gamma smaller than 1? It tells you something about the physics, the geometry, or it's just
yeah.
Thanks.
I'm not too involved with the theory of the modified gravity, but basically the idea of these modified gravity theories is that you can map the parameters, the free parameters of the theory into this gamma which is the ratio between these 2 potentials, right? So depending on the modified gravity theory that you have different parameters, and this basically will give an intuition if the parameter is higher or lower. But I think will depend on the theory that you choose. But yeah.
That was not originally motivated by dark energy. That's from the early GR theories. Okay, thank you, João Pedro. Let's think again. And now our last speaker, Ramses.
Sorry to the English speaker because I will present my talk in Spanish. Hola a todos, buenas tardes. Gracias por quedarse hasta la última charla. Me imagino que están cansados. Mi nombre es Ramses. Realicé el magíster en la Universidad del Paraíso bajo la supervisión de la doctora Verónica Motta, en la cual pudimos determinar o estimar los parámetros del disco de acreción de un par de sistemas, pero en particular voy a mostrar los resultados de los parámetros del disco de acreción en lo que es la cruz de Einstein. Se me olvida que tengo el retorno ahí arriba. Ok, como mencionaron mis compañeros anteriormente, el efecto de lente gravitacional se produce por el potencial gravitatorio de un objeto masivo, ¿ya? Deflectando la luz que proviene de una fuente lejana, como por ejemplo es un quasar. En particular hay que tener en consideración que resolver un disco de acreción es algo muy complejo. Si se fijan acá la escala en la cual el tamaño en arcos segundos es del orden de 10 elevado a menos 3. Recientemente, hoy en día, el telescopio que alcanza una resolución relativamente considerable es el James Webb Telescope, pero este solo alcanza una resolución angular de 0.1 segundo, por lo tanto es una tarea muy difícil poder resolver como tal el disco de acreción. Lo que observamos en el espectro de un quasar, particularmente, es una emisión proveniente del continuo una emisión de continuo proveniente del disco de acreción y una mezcla entre líneas estrechas y líneas anchas de emisión proveniente de la región de emisión de líneas estrechas y emisión de líneas anchas respectivamente. Y bueno, un fenómeno o un efecto que podemos observar también en el macromodelo es efecto microlente, donde objetos compactos o estrellas localizadas en la galaxia lente producen múltiples imágenes de la fuente. Esto altera el flujo tanto del continuo e incluso algunas veces en la parte ancha de la línea de emisión. Nos interesa medir estas anomalías en el flujo, las cuales las medimos a partir de la diferencia de magnitudes. Por lo tanto, ¿De qué forma o cómo podemos resolver estos objetos que son compactos, que son muy lejanos y que a su vez tienen una resolución angular muy pequeña? Entonces, en este trabajo presento lo que se conoce como efecto microlente cromático, ¿ya? A partir de las observaciones de los espectros y de los datos fotométricos que obtuvimos de la literatura. El sistema en particular es la cruz de Einstein, o el más conocido como 2237, es un sistema bastante estudiado, porque la galaxia lente se encuentra un redshift, entre comillas, cercano, y particularmente las imágenes del quasar, las 4 imágenes de este sistema, se forman en el bulbo de la galaxia lente. Por lo tanto, significa que son muy propensas a estar afectadas por efecto microlente. Y de hecho, en este sistema se detectó efecto microlente por primera vez. Nuestros datos o la colección de datos que obtuvimos, que analizamos, corresponden a espectros de X-Shooter que van desde el ultravioleta hasta el visible. Estos fueron reducidos por la pipeline y a su vez fueron corregidos por absorciones telúricas. También tenemos datos en banda estrecha obtenidas por el Nordic Optical Telescope, los cuales están publicados por estos autores, y también datos de la base de datos de Castle, que fueron observaciones obtenidas por el telescopio espacial. Por lo tanto, nos interesa analizar el espectro. Esto es prácticamente como una receta a seguir. ¿Ya? Lo primero es obtener el espectro aprovechando la configuración de la slit en las imágenes. Dado que la separación de las imágenes del quasar es mayor a un arcosegundo, es posible separar o extraer cada una de las componentes en un espectro completamente individual. Para ello, ajustamos funciones mofatianas al espectro y también realizamos un enfoque de Monte Carlo para poder determinar la incerteza en el flujo y en los parámetros ajustados de la función mofatiana en este caso. Por lo tanto, el espectro en unidades arbitrarias, como dice aquí, no utilizamos el espectro calibrado en flujo, dado que estamos calculando la razón de flujo para obtener la diferencia de magnitudes. Muestra una variedad de líneas de emisión desde el ultravioleta hasta el infrarrojo cercano. Por lo tanto, para todas las líneas de emisión que aparecen aquí, la más prominente principalmente, seleccionamos aquí un ejemplo, graficamos o fijamos una función lineal que represente el continuo bajo la línea de emisión para las 4 líneas, con la finalidad de obtener el flujo bajo la línea de emisión y determinar esta diferencia de magnitudes con respecto a la imagen más brillante, que en este caso es la imagen A. Es el paso que aplicamos para el continuo. Para la línea de emisión procedemos de una forma similar, removemos el continuo, dejamos las líneas de emisión sin continuo, aquí están normalizadas por un cierto valor, solamente para observar algunas diferencias o anomalías, integramos el núcleo de la línea de emisión, dado que el núcleo o el core está relacionado a la región de líneas estrechas. Y esta emisión se produce en regiones mucho más externas al disco de acreción, por lo que consideramos que no deberían estar afectadas por efecto microlente. Por lo tanto, consideramos que esta diferencia de magnitudes en el núcleo de línea de emisión debería ser constante. Nos interesa cuantificar o medir cuánto es la diferencia o cuánto es lo que estaría afectado a los continuos con respecto a la línea de emisión o a la diferencia de magnitudes de la línea de emisión. Dado que, como mencionaba, estas líneas de emisión no se verían afectadas por efecto microlente. En este gráfico muestro los resultados de las diferencias de magnitudes. En azul, acá tenemos la diferencia de magnitudes de las líneas de emisión. Y podemos observar que los continuos en naranjo aquí, el cuadrito en naranjo, corresponden a los continuos o el flujo bajo las líneas de emisión. Un poco más arriba tenemos la época de datos que corresponden a las observaciones de Mosquera et al. 2009, perdón, y el continuo asociado a las observaciones de Castle. Entonces tenemos 3 mediciones de mediciones de continuo en las cuales observamos que estas están desplazadas con respecto a las líneas de emisión. Por lo tanto, detectamos efecto microlente. Es el segundo paso importante. Al medir las diferencias de magnitudes entre el continuo y el núcleo de línea de emisión, observamos también de que hay una variación que depende de la longitud de onda. Esto va disminuyendo a medida que me voy acercando a la región más externa del disco de acreción. Y la razón de esto es que la primera parte está mucho más al interior del disco de acreción, por lo tanto estaría mucho más afectada por efecto microlente. Mientras que en regiones externas, las variaciones mucho pequeñas, o incluso acá no apreciamos efecto microlente, pero sí, por ejemplo, con la época de los datos de Castells. Así que esto concluimos que hay cromaticidad, hay efecto microlente cromático y hay una dependencia en la longitud de onda. Esto nos permite modelar el disco de acreción con un perfil de temperatura, dado que un perfil de temperatura con una ley de potencia, este parámetro lo definimos como P, y el tamaño característico del disco de acreción es proporcional a la longitud de onda elevado a este perfil de temperatura. Comparamos nuestros datos o el perfil de temperatura con un modelo de Shakura-Sunyaev, que es el modelo de disco delgado. Entonces, ahora que ya obtenemos nuestras mediciones y para cada par de imágenes, estamos considerando que hicimos el mismo procedimiento para B-A, como tenemos indicado acá arriba, B-A, C-A y D-A. Este es solamente un ejemplo de los 3. Nos interesa poder simular el efecto microlente para poder reproducir las diferencias de magnitudes observadas en las longitudes de onda en donde establecemos el efecto microlente cromático. Estas longitudes de onda son los valores que están aquí, me olvidé de mencionarlo anteriormente. ¿Ya? Utilizamos el modelo, gracias, utilizamos la distribución de materia en la galaxia lente de la literatura, obtenemos capa y shear, que anteriormente explicó Carla, y construimos los mapas de magnificación, construimos los mapas de microlente a través del Inverse Polygon Mapping. Esto significa en el fondo de que lanzamos aleatoriamente una distribución de estrellas en la galaxia lente para crear estos mapas de magnificación para las 4 imágenes. Consideramos también un 100% de estrellas en materia bariónica y una masa promedio del orden de 0.3 masas solares. Por lo tanto, lo que queremos hacer es convolucionar este disco de acreción a estas 3 longitudes de onda con la finalidad de poder reproducir estas diferencias de magnitudes observadas con el modelo de microlente. Así que realizamos la estadística y comparamos nuestras observaciones con el modelo, incorporando las incertezas previamente obtenidas. Finalmente, determinamos la probabilidad conjunta para las 9 finales estimaciones de los parámetros del disco de acreción, para así obtener una única medición de 9 mediciones independientes, determinamos finalmente una con la probabilidad conjunta. Así que por lo tanto, obtenemos 3×3, o reproducimos, mejor dicho, 3×3 funciones de densidad de probabilidad. Nuestros datos arrojan un máximo aproximadamente con un perfil de temperatura de 0.53 y un tamaño del disco de acreción aproximadamente de 27 días luz. Por supuesto que queremos comparar también estas mediciones con trabajos previos, como por ejemplo el trabajo realizado por los autores Jiménez Vicente et al. 2014, en el cual ellos realizan o obtienen un tamaño promedio del disco de acreción utilizando 8 sistemas. Sin embargo, uno de las estimaciones del disco de acreción está en buen acuerdo con nuestras estimaciones de los parámetros del disco de acreción. Por lo tanto, como conclusión, utilizamos un método indirecto para poder observar o resolver el disco de acreción, obtener su tamaño y obtener un perfil de temperatura. Es muy complejo obtener imágenes directas, hasta ahora no se ha hecho, salvo que sea un objeto muy cercano, lo que sucedió, por ejemplo, con M87. A partir del análisis espectral también obtenemos la diferencia de magnitudes y con esto la existencia del microlente cromático. Y finalmente, al comparar nuestros resultados, está de acuerdo con estimaciones previas del disco de acreción, así que con eso estamos contentos. Así que muchas gracias.
Preguntas.
Sorry, I'm going to ask it in English.
Okay.
Very nice talk. Do you have an idea on how many sources you can do this work on?
Can you repeat me the question,
Sí,
please?
ok, voy a intentar en español entonces.
Okay, eso.
¿Y sabes más o menos cuántas sorgentes puede hacer el mismo trabajo?
¿Cuántas
Fuentes, cuántos quasars, no sé.
en cuántas fuentes se puede realizar? Bueno,
Sí.
va a depender principalmente de que si se puede detectar efecto microlente cromático, ¿ya? Porque necesitamos que haya una dependencia en la longitud de onda para poder caracterizar el disco de acreción con un perfil de temperatura. Hemos obtenido mediciones en otros sistemas donde la diferencia de magnitudes o la separación entre la línea de emisión y el continuo es constante. Entonces no podemos en este caso definir una cromaticidad y por ende no podríamos utilizar el método como tal.
Y yo tengo una pregunta.
Okay.
Una de las últimas frases que ha dicho es que los parámetros del modelo del disco estaban buenos comparados a resultados anteriores de otras fuentes, ¿cierto? Pero ¿cómo se comparan las incertidumbres del trabajo que has hecho tú con el Chromatic Lensing con los otros trabajos puntados, no sé si con radio X, radio o de dónde vino
Sí,
el modelamiento del disco?
Sí, de hecho, el trabajo anterior está basado en observación en infrarrojo principalmente. ¿Cómo se comparan las incertidumbres o las incertezas? ¿Puedo responder que realmente no lo sé o no sé esa respuesta como tal? No sé si vuelvo a la figura. ¿Cómo se retrocede?
El de abajo, el todo.
Vale. Me pasé. Ahí. Bueno, la incerteza en este caso están también dentro acá. La incerteza, bueno, este es el puntito azul que corresponde a distintos enfoques estadísticos en el cual el autor, o los autores, mejor dicho, realizaron las estimaciones. Así que estando dentro de la incerteza de nuestras mediciones, que son el triángulo rosado y en azul, consideramos que es un buen ajuste o consideramos que el modelo
Estos puntos todos son de Chromatic.
sí, principalmente, por ejemplo, el promedio que aparece acá también es con cromaticidad. Y estos dos que están acá, que son de los autores, Jiménez Vicente también con cromaticidad, pero utilizando enfoques estadísticos completamente distintos.
O sea, no hay estudios de este disco en técnicas más tradicionales.
Como por
Está
ejemplo.
muy lejos, imagino.
Pero en este caso, ¿como qué técnicas tradicionales?
Con los
Bueno,
aerosoles.
este sistema en general ha sido muy estudiado, de hecho, dado que fue el primero donde se ha detectado efecto microlente, ya, pero sí hay otras estimaciones basadas en observaciones en distintos rangos de longitud de onda, como tal.
¿Más preguntas? Questions? Preguntas? We are a little early, but let's thank Ramses and all the speakers of the session.